Welcome to the Introduction to Calculus Final Exam Review. While this exam is a comprehensive exam, it's mostly going to be weighted towards the later topics we covered. So that would be things like integration, Riemann sums, antiderivatives, and then a little bit the further we go back in the course. Now, before we begin, I just wanted to explain why I'm making this video. I wasn't originally planning to because we have a comprehensive review that we're doing for the final exam to prepare everybody, but I received a lot of emails asking me to do this because people have said that the other videos were really helpful, so hopefully this one will be as well. So let's jump right into our final exam review that we did in class, but also now that you can follow this. The first question says, estimate the area under the graph of f of x equals 5 plus 2x cubed from x equals -1 to x equals 2, using the right-hand endpoints and the given number of rectangles. So what we're going to do first is I'm going to write down what our function is. So our function is f of x equals 5 plus 2x cubed, and we're going from interval from -1 up to 2. So in this case, what we're looking at for the first part, A, is we want to have R3, which is just going to be breaking this function into 3 rectangles using our Riemann sums, which are the sum I equals 1 to 3, delta x, f of x sub I, where x sub I is the index. And because this is R, this means we're using right-hand endpoints. So for example, if we had some shape like this, and we broke it into 3 intervals, we would be using the right-hand endpoint of each interval to create our rectangles that we're using to approximate what the area of this graph would be. So the first thing we want to figure out is we want to figure out what is this delta x. So delta x is just going to be the change in our x over the number of values that we have. So this is how many subintervals. So this is going to be b, your endpoint, minus a, your starting point, divided by n. So if I just wanted to label this would be b, this would be a. So plugging in what we have that we're going from 2 to -1. So this is going to be 2 minus -1, which of course will just be plus 1, divided by our 3 subintervals. So this is going to be 3 over 3, or a change of 1. Next, what we want to do is we want to figure out what are our actual intervals that we're doing this Riemann sum over. So we're going to start at our starting point A. So this is going to be starting at -1, and then we're going to change by our amount delta x. So we're going to go up by 1 up to 0. For the second interval, we're going to start at 0. We're going to go up by 1 again, so up to 1. And then for the third interval, we're going to start at 1, and we're going to end at 2. So now that we know what our intervals are, we can look at what our right-hand endpoints are. For the first interval, it's 0. For the second interval, it's 1. And for the third interval, it's 2. So this means we can now, if we think about our rectangles, what we're really looking at is we're trying to figure out the width times the height. So we have our width. Our width is just delta x. So in this case, this isn't the shape, but pretend it is. The width would be, in this case, 1. So now how do we find our height? Well, what we do is we go to our right-hand endpoint. We go up to our curve, which means we plug it into the function that we have, and this will give us the height using the right-hand endpoint of this interval. So we're going to find the heights by plugging in f of x1, f of x2, and f of x3, because we have 3 subintervals, which in this case would be f of right-hand endpoint, 0, f of 1, and f of 2. Plugging this in to our original function, right? If I plug in 0 into this, I'll get 0 cubed is 0, times 2 is still 0, so I will get this first height is 5. For the second interval, I'll plug in 1, so 1 cubed is 1, times 2 is 2, 5 plus 2 is 7. And for my third 2, I plug 2 in, I get 2 cubed, which is 8, 2, 4, 8, times 2, which is 16. 16 plus 5 is 21. So now it's time to actually solve for our area. So the area, using our right-hand endpoints with 3 subintervals, is going to be the sum I equals 1 to 3, delta x, and then f of x sub I, where I'm going to plug in delta x, which is just equal to 1, times 5, plus delta x, which is 1, times 7, and then 1 times 21. Because all of these have the same delta x, I'm actually going to pull this out. So this would end up being 1 times, and then I just plug my heights in. 5 plus 7 plus 21, which is going to give me 33 times 1, which is just 33. What about if I want to do the same thing, but now I want to have 6 subintervals using my right-hand endpoints? So again, this is going to be the sum I equals 1, but now we're going up to 6 subintervals, delta x and f of x sub I. So let's figure out what our delta x is. So our delta x, which is just the widths, is going to be b minus a over n. Well, we know our b minus a is just going to be equal to 3, but now we have 6 subintervals, so this is going to be divided by 6, which is going to give us a change of x of 1/2. So now let's look at our intervals. Our intervals are we're still going to start at -1, but now we're going to go up by 1/2. So in this case, we go up from -1, we get -0.5 or -1/2, depending on which way you want to keep it. I'm going to do decimals. So -0.5. Then we're going to start at -0.5. We're going to go up by 1/2 again, or 0.5, and this will get us to 0. Then from 0 to 1/2, or 0.5. Then from 0.5 up to 1. Then from 1 up to 1.5. And then finally from 1.5 up to 2. So now we have all of our intervals. We can figure out what are our actual heights, right? Because we're going to be using right-hand endpoints. We're going to have this one, 0, 0.5, 1, 1.5, and 2. So our heights are going to be f of -0.5. They're going to be f of 0, f of 0.5, f of 1, f of 1.5, and f of 2. So now plugging each of these in, what do we get? Well, if we plug in -0.5 into, I'm actually going to cheat and I'm going to use the fractions for when I do it. So if I have, this is -1/2, then -1/2, when I cube it, is just going to cube the bottom, because 1 cubed is just 1, 2 cubed is going to be 8, so this is going to be -1/8 times 2, so -2/8 is going to give me -1/4. So this is going to be +5. So I'm just going to write this down as 5 minus 1/4. If I plug in 0, same thing before, this term becomes 0. This is just going to be equal to 5. If I plug in 0.5, it's going to be the same thing as when I plugged in -0.5, except this will now be positive. So this will be 5 plus 1/4. We can figure out what this is after. If I plug in 1, I'm going to get the same thing as when I did 1 here, and I'm going to get 7. So now if I plug in 1.5, which is 3/2, plugging this into this, I'm going to get that this is equal to 27/4. And then if I plug in 2, I'm going to do the same thing I got before. So now that I have each of the heights, I can figure out what the area of each rectangle is by taking my delta x, that's the width, times the heights. I'll sum all these up and I'll get my area. So my R6, which is my Riemann sum with 6 subintervals, is going to be equal to delta x times whatever 5 minus 1/4 is, plus delta x, so 1/2 times 0.5, plus 1/2 times this. Every single one of these terms has 1/2, so I'm going to pull this out. So I'm going to be left with 5 minus 1/4 plus 5 plus 5 plus 1/4 plus 7 plus 27/4 plus 21. And you might wonder, why did I just leave it as 5 minus 1/4 instead of figuring out what 5 minus 1/4 is? And it's because I actually knew from doing this the other day that these two were just going to end up canceling. I have -1/4 here plus 1/4. So if I take 5, 10, 15, 22, 22 plus 21 is going to give me 43. And then I just have to figure out what 43 plus 27/4 is. And I'm going to get that this is equal to 23.375. Now you might notice when comparing these two, when I did 3 subintervals, I had an area of 33. But when I had 6 subintervals, I had an area of 23.375. So what this means is that as I'm taking more and more subintervals, we're approaching what the actual area under the curve is, right? Because when I have 3 subintervals, in this case, it looks like I'm overestimating, and I'm getting closer and closer until I reach my actual area, which is going to be the limit as n approaches infinity, sum I equals 1 to n, delta x, f of x sub I, where I'm basically doing what I'm doing right here, except for I'm going to take more and more and more and more subintervals until the area or the width becomes equal to 0, and I'm going to get an infinite number of infinitesimal rectangles to give me to actually zero in on the actual area under this curve. For question 2, I drew a graph here, and we're going to be trying to figure out what the area under the graph is using right hand and left hand endpoints. So you can see it's not the best drawing compared to what you would see on the screen, but we're just trying to look at how we would do this graphically if we don't know what the actual function is. So problem 2 says, the graph of g is shown. Estimate the integral from -3 to 3, g of x dx with 6 subintervals using left and right hand endpoints. So we have the integral from -3 up to 3, our function g of x, which is this graph here, dx. Now you'll notice that it's -3 to +3, but I have 6 ticks here. That's because every single one of these represents a change of 1. And this is just so we could kind of break it out a little bit more to make it a little bit easier to do the problem on the actual practice. So first things first, let's do our left-hand endpoints. So our first interval is going to be from -1 to 3 up to -2. So we have a difference of 1. So this is our first subinterval, but using left-hand endpoint, this means I'm going to be making a rectangle by going up from here, creating my rectangle for this particular interval. Then for my second interval, from -2 to -1, I'm going to, at -2, my left-hand side of this interval, I'm going to go up to my function, and I'm going to create my rectangle. For 1, I'm then going to do the same thing. I'm going to use my left-hand endpoint. I'm going to go down to the interval, and I'm going to go to 0, which will give me my rectangle. For interval 3, which is from 0 to 1, do the same thing. I'm going to go down to where the graph is, and then I'm going to go over and create my rectangle. And then I have from 1 to 2, go down to my graph, create my rectangle. And then for my last interval, which is from 2 to 3, I'm going to go down to my function, and then I will create my rectangle. So now we just got to figure out what the area of each of these are. So I'm just going to kind of estimate these here. But for my first interval, it looks like my height is about, I'm going to say, let's say 2.2. So for left-hand side with 6 subintervals, I'm going to put 2.2 plus. This one looks like it goes to about 1, so I'm going to just put 1 just to make it easy. My third rectangle goes down to negative about 1.3. So anything that is below your x-axis, you are subtracting. This is negative. Anything above, we're going to add because it's positive. So for my fourth rectangle, it looks like it goes down to about negative 1.5. No, it looks like it actually hits the line. So negative 1, yeah, so negative 1.5. My next one, I'm going to go down to, it looks like about negative, I don't know, I'm going to say 1.6. And then my last rectangle is going to go down to, I'm going to say this is negative 0.5. Remember, because each of these ticks is 0.5. So 0.5, 1, 1.5, 2. So now in order to find this, we're just going to add and subtract all of these areas to see what the final area is of this function. So what I'm going to do is I'm actually going to use my calculator because I don't want to make any silly math mistakes. So I have 2.2 plus 1 minus 1.3 minus 1.5 minus 1.6 minus 0.5, and I get a total of negative 1.7. Now, because I'm doing this sort of ad hoc like this, your answer may vary. For example, when I did the original practice exam problems with my students, I actually got a value of negative 1/2 because I kind of was rounding values, but I also had this actual graph so I could, follow the lines a bit easier. So for the next part of the problem, we want to try to do the same thing, but we're going to use right-hand limits. So in this case, what we're going to do is we want the right-hand area. So for this first interval, I'm now going to start at -2, and I'm going to create my rectangle. For the second one, I'm going to start at -1. I'm going to create my second rectangle. So for the first one, I'm at my first rectangle. For my third interval, I'm going to go down to the function and create my third rectangle. For my fourth interval, I'm going to go to my right-hand side, go down to the function, create my rectangle. For the fifth interval, and then for the sixth interval. And then we'll do the same thing. We're going to figure out what each of these heights are. So this first one, I'm just going to say this is equal to 1. For my second one, I'm going to say this is equal to negative 1.3. For my third interval, I'm going to say this is equal to negative 1.5. At least I'm kind of being consistent. My fourth, I'm going to have another negative 1.5. For my fifth, I'm going to have this is equal to about negative 1.2. No, sorry, this is about negative point. So this is 0.5, negative 0.6. And for my last interval, I have a height of 2.5. So plus 2.5. So then again, what I'm going to do is I'm just going to use my calculator to make sure I don't make any stupid math errors. So it's going to be 1 minus 1.3 minus 1.5 minus 1.5 minus 0.6 plus 2.5. And doing this, I get an area of negative 1.4. So looking at these, you can see that using my left-hand endpoints, I have negative 1.7. For my right-hand endpoints, I have negative 1.4. So it looks like this one is actually probably below the value at negative 1.7. This one is likely above the value at negative 1.4. And then if I were to take the midpoint, it likely would be somewhere in between these. But the idea of this is if I were to break this into more and more subintervals, what should happen is my left-hand endpoints, which are underestimating, my right-hand endpoints, which are overestimating, should converge on the actual area under the curve, where we're adding up any part that is above the axis and subtracting any part that is below the axis. Problem 3 says we have a table of values of an increasing function f is shown. Use the table to find the upper and lower estimates for the integral from 10 to 30 f of x dx. And I've written out the table here and the function that we have. So as I was talking about previously, anytime we have some curve or function and we're using left-hand or right-hand endpoints, what's going to happen is that we are going to overestimate for one and underestimate for the other. And then as you get more and more and more subintervals, it will converge on the correct value. So what this is asking us to do is it is asking us to figure out what is the area of the curve using right and left-hand endpoints and seeing what the values would be for the one that underestimates the value and the one that overestimates the value. Normally what I would do is I would actually just do each of these and figure out which one's which, but I already know that this one is going to be my left-hand side endpoints, and this one is going to be my right-hand side endpoints. So now what we're going to do is we're going to figure out what are our intervals. And this is going to be the same for both of these. We're going to start at 10, and we're going to go up to 14. And then our second interval will be from 14 to 18. Our third interval will be from 18 to 22. Our fourth interval will be from 22 to 26. And our last interval will be from 26 up to 30. Now we can actually figure this out pretty simply, because if we want to know what our delta x is in this regard, well, all we have to do is we just have to look up how much are we changing in each of these. Well, I'm changing from 10 to 14, which is a difference of 4. 14 to 18, difference of 4. So my delta x, or the width of each rectangle, is going to be 4. And now we can actually solve this right away, because when we want the area using our left-hand endpoints, what we're going to do is we're going to use 10, 14, 18, 22, and 26, and we're going to use the associated values for the height. So I know that I have, for my sum, I equals 1, 2, 1, 2, 3, 4, 5. I have 5 intervals. Delta x, f of x sub I. I know that I can pull this delta x out, so I'm going to pull my 4 out. So this is going to be 4 times, and then I just have to figure out what is the height when I have the time of 10 seconds. It's negative 12. Minus, now for the next one, 14, I have negative 6. So plus negative 6, so minus. For 18, I have negative 2. For 22, I have plus 1. And then for 26, I have plus 3. So then adding this all up together, negative 12 and minus 6 is negative 18, negative 20. Negative 20 plus 4 is going to give me negative 16. Negative 16 times 4 is going to give me negative 64. Now let's do the same thing with our right-hand endpoints. So for our right-hand endpoints, we're going to be using the right side of each of these intervals. So same idea. I'm just going to set this one up. My area is equal to 4 times. So for my first interval at 14, I have negative 6. For my second interval at 18, I have negative 2. For my third interval at 22, I have plus 1. For my fourth interval at 26, I have positive 3. And for my last interval at 30, I have positive 8. So then, of course, adding all this up together, I have minus 6 minus 2 is going to give me negative 8. Negative 8 and positive 8 are going to cancel. This is just going to leave me 4. So 4 times 4 gives me an area of 16. So you can see that when we're using our left-hand endpoints, we're actually underestimating the area of this curve at negative 64. When we're using our right-hand endpoints, we're overestimating at positive 16. So when I first did the problem, how did I know that the left-hand endpoints should be the one that underestimates? And it's because when we read the problem, it says we have an increasing function. So let's say we have some function, it's increasing, whatever it is. Well, if I'm using left-hand endpoints, that means for my first interval, I'm going to start really low, right? Basically 0 if it's starting at 0, just for the example I'm giving. And then my second interval, I'm going to have something like this, my third interval, my fourth interval. And basically what's going to happen is if I have an ever-increasing function, the left-hand endpoints will always underestimate. If I have an increasing, if I'm using right-hand endpoints, then for this first interval, I would have my rectangle look like this. My second, it would look like this, 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 and this, which means that my right-hand endpoints will always overestimate. So my left-hand endpoints, underestimating. My right-hand endpoints, overestimating. And of course, as I get more and more and more subintervals, these values will converge on the actual area under this curve. Problem 6, we have a graph of f shown in this image. We want to evaluate each integral by interpreting in terms of area. So you'll see that we have 4 integrals we're going to find here. For the integral from 0 to 2 on this function, the integral from 2 to 6, the integral from 6 to 7, and then finally the entire integral from 0 to 7. So pretty much what we're doing is we're looking at the fact that if we have some graph, in this case it looks something like this, then what's happening is we're going to find the area of this first interval. That's our 0 to 2. Then we're going to find the area of the second interval. Then we're going to find this area of our third interval. So we'll call this one A1, A2, and A3. And we're going to use the fact that if I want this entire integral from starting point to the ending point, what I can do is I can use the area of the first, second, and third to figure out what this area is, where anything above the x-axis is positive, anything below is negative. So looking at our graph, you can see that our first is going to be a triangle. So using a triangle, we have that for a triangle, the area is 1/2 base times height. So we're going from 0 to 2, so we have a base of 2. From the y-axis, we're going from 0 to 4, so we have a height of 4. So this is going to be 1/2 times 2 times 4. The 1/2 and the 2 will cancel. We'll just be left with an area of 4. So that would be the area of the rectangle, kind of like this. Now we go to the next part of our graph. We have a semicircle. So the area for our semicircle is going to be using pi r squared. So we have pi r squared, which would give us the area of a circle. But because it's a semicircle, we only have half the circle. So of course, we're going to multiply this by 1/2. So now what we're going to do is, looking at this graph, it goes from 2 up to 6, right? If you look at our integral, it goes from 2 to 6, which means this would be our diameter. We have a diameter of 4, which means we have a radius of 2. So this is going to be 1/2 pi 2 squared. So 2 squared is 4, divided by 2 is going to give me 2 pi. And I think in class, I just rounded pi to 3.14 just to make it quick. I'm actually just going to leave it as 2 pi for this one. Now, because area 2 is under the y-axis, the z-axis, this is going to be minus 2 pi. Now, for our third interval, we have another triangle. This one has a base of 1. This one has a height of 1. So this one is going to be 1/2 times 1 times 1, which is just going to give us 1/2. So finally, if we wanted to bring all of this together to figure out what the entire area under this curve is going to be, we're just going to take area 1 minus area 2 plus area 3. So we're going to get 4 minus 2 pi plus 1/2. And like I said, in my class, what I actually did is I just rounded 2 pi to 2 times 3.14. And so when I did this, I got a value of negative 1.78, just to get an approximate answer. For problem 5, we have a graph of a function g given, where we want to estimate the integral from 0 to 8 on our, I put f of x dx in the problem, but it should have been gx dx, with subintervals using right-hand side, left-hand side, and midpoints. So using the right-hand sides, I didn't actually put in the problem how many subintervals to do. So what I'm going to do is I'm going to cheat and I'm going to do subintervals of 1 just to make it easy, because that way I'll have a delta x of 1, right? Because that way each interval will just have a width of 1. So for my first one, I'm going to create a rectangle. I'm going to go up and I'm going to create my rectangle using my right-hand side. Then I'll do it for my second subinterval. I'll do it for my third subinterval, my fourth subinterval, my fifth subinterval, my sixth subinterval, my seventh subinterval, and then my eighth subinterval. And then I just had to figure out what the height of each of these are, because my delta x is just going to be 1. So this is just going to be equal to an area of, this one is 3, right? So this is 2, this is 3. So we have a height of 3 plus, this one has a height of 1. This one has a height of, let's say, I don't know, 2.1. It's actually supposed to be 2, I think, but this one looks like at about 2.5, 2.4. This one has a height of about, I'm going to say 1.5, minus a height of negative 1.3. This one has a height of about negative 1.7. And this last one has a height of negative 1. And then again, I'm going to actually plug this in my calculator to make sure I don't make any silly mistakes. So I'll just add up 3 plus 1 plus 2.1 plus 2.4 plus 1.5 minus 1.3 minus 1.7 minus 1, and I get an area of, wow, that actually worked out well. I got an area of 6. Now we're going to do the same thing for our left-hand side. So I'm going to pick a different color just to make this one stand out a little bit. So looking at my left-hand side of each subinterval, this one for the left-hand side starts here. And then for this one, it's going to go up to the curve, and we're going to have this rectangle. We're going to have this rectangle. We're going to have this rectangle. We'll have this rectangle. Then we'll have this rectangle. See what's happening in each of these subintervals when I'm going to the left is I'm just going up to the curve or down to the curve, depending on which side I'm on. And I'm creating a rectangle from there. So if we were to look at this then, my area would be 2 plus 3 plus 1. So on this one, I'm doing left-hand side, so I'm up to here. This one looks like about 2.2. This one looks like about 2.6. This one looks like about, I'm going to do 1 again. Then we have that it goes down to negative 1.3, let's say. And my last one is going to go down to here, which is about negative 2. So again, I'm going to add all these up and see what my area is using my left-hand side. So this is going to be 2 plus 3 plus 1 plus 2.2 plus 2.6 plus 1 minus 1.3 minus 2. And I got an area of 8.5. Now for my last one, I'm going to use green because it's a pretty vibrant color. And this one I'm going to be using midpoints. So instead of using the left-hand side or the right-hand endpoint of this interval, I'm actually going to use the midpoint, which if I go up to my graph will give me a rectangle like this. For my second subinterval, I'm going to go up to my function and I'm going to get a rectangle like this. For my third midpoint, I'm going to get one like this. For my fourth, I'm going to go here, get a rectangle like this. For my fourth, I'm going to get rectangle like this. For my fifth, it looks like it's actually right on the line, so that actually works out pretty well. For this one, I'm going to get a rectangle to here. And then for my last subinterval, I'm going to get a rectangle like this. So you can see that by taking the midpoint, I'm going to get different rectangles than the other ones that I did. So let's do it. Okay, so this one looks like it's about 2.6. So area equals 2.6 plus this one looks like about maybe 2.4 plus this one looks like about 1.6. This one looks like it's about I'm going to say 2.5. This one's about 2.3. Then we're at this one, we have 0. This one has a height of -2. And my last one has a height of, I'll say -1.6. So then just to make it a little easier, I do notice though quickly that this -1.6 and this +1.6 cancel with each other. So that'll make it a little bit easier to calculate this. So again, I'm going to go back to my calculator and I'm going to get 2.6 plus 2.4 plus 2.5 plus 2.3 minus 2. And I'm going to get an area of 7.8. So if we compare how these different areas look, it looks like when I'm doing my right-hand side endpoints, I'm underestimating with a value of 6. When I'm doing my left-hand side endpoints, I'm overestimating with 8.5. And then my midpoints give me a value that's kind of in between, which means it's probably closer to the actual area. And again, if I were to continue taking more and more subintervals, making these widths smaller and smaller and smaller, more and more rectangles, I would converge on the real answer, which is probably somewhere in the 7s range based on the fact of my underestimation and my overestimation of the area under this curve. Problem 6 says use the midpoint rule to solve the integral from 2 to 10 square root of x cubed plus 1 dx with n equals 4 intervals. And we're going to round our answer to 4 decimal places. So we have the integral from 2 to 10, and then we're going to take the square root of x cubed plus 1 dx. Now the fact is we have 4 subintervals, so just like before, we're doing Riemann sums. So our delta x in this case is going to be b minus a over n, where b is going to be 10, a is going to be 2, and n is going to be that number 4 from our problem. So we're going to have 8 divided by 4 is going to give us an interval width of 2. So now we'll just figure out what our intervals are. Starting at our starting point 2, our intervals are going to be 2 plus 2 is going to be 2 to 4, 4 to 6, 6 to 8, and 8 to 10. Now we're using our midpoints here, so this means what we're actually going to be doing is we're going to be plugging in the values between 2 and 4, 4 and 6, 6 and 8, and 8 and 10. So that means that when we're finding our heights, this is going to be using f of, so the midpoint between 2 and 4 is going to be 3. F of 5, f of 7, and f of 9. What we're going to do now is we're going to plug each of these values into this to figure out what the actual heights are. So the first one, we're going to get 3. 3 cubed is going to be 27, right? 3 times 3 is 9, times 3 is 27, plus 1. So this will be the square root of 28. For 5, we're going to plug this in. So 5 times 5 is 25, times 5 is 125. So we're going to get the square root of 125. 126, I forgot to add the 1. For 7, we're going to plug 7 in. I'm not sure what 7 cubed is off the top of my head. So the next interval, we're going to plug in 7. So 7 cubed is going to be 343 plus 1, so 344. So square root of that. And then for the last interval, we're going to plug in 9. 9 cubed, by the way, I'm not doing these in my head. I'm checking these beforehand. So 9 cubed is going to be 729 plus 1, so 730. So this is going to be the square root of 730. So now what we're going to do is we're going to take the area of each of these by taking the width of each rectangle times the height. So each of these has a width of 2, so I'm going to pull that out. So area is going to be 2 times the square root of 28 plus the square root of 126 plus the square root of 344 plus the square root of 730. Now this question does want to get an approximate answer because it did say to round to 4 decimal places. If we do that, this is going to be equal to 2 times, I have the values here as 5.2915 plus the second one I have 11.2249. The next one I have 18.9 0.5472. And then the last one I have 27.0185. So I'm just going to plug all this in my calculator, and I'm going to see what our actual area is using 4 subintervals and the midpoint method. So plugging this in, I got a value of 124.1644. Now, one thing I do want to point out is when I did this in class, I used these values here. So I had the 4 decimal approximations, and I used those. When I calculated this here, I actually used the square roots, which means I didn't have the rounding error while I was doing the calculation. So it differs a little bit from the solution that I did before, which was I had 124.1642. But you can see that it made a very minor difference by either using the square roots versus the rounded errors. But if you want to be more precise, I would suggest using the square roots. So now at this point, we're done with all of the Riemann sum and graphing problems. So I know it's kind of heavy with the graphing problems, and that's because I really wanted to kind of focus on understanding the idea of our Riemann sums and what they're showing, and graphically what this means by using our left-hand endpoints versus right-hand endpoints versus our midpoints, and how that then leads us to solving integration. So next we're going to be focusing on some problems with antiderivatives, again, building up to our final subtopic of integration. Problem 7 says, find the most general antiderivative of the function and use c for a constant of the antiderivative. So our original function for problem 7 is f of x equals 6x to the 7th power minus 3x to the 4th power plus 12x squared. So remember, when we're doing our antiderivative, it's sort of doing the inverse of our power rule. So in this case, with our power rule, whenever we did a power rule doing derivatives, we would bring down the power and we would then subtract 1. So for our antiderivative, which we're going to write as capital f of x, we're going to leave our constant. Now this 7 is going to go up by 1. So this is going to be x to the 8th, and then we're going to divide by that 8. For the next one, we're going to have our minus 3. This x to the 4th becomes x to the 5th, and we're going to divide by 5. And then our last one, we're going to have the plus 12. This x squared is going to become x cubed, and then we're going to divide by 3. And now what we need to do is we just need to clean this up. So in this case, we have 6 over 8, which is the same thing as saying 3/4 x to the 8th power minus 3/5 x to the 5th power plus 12 divided by 3 is going to give me 4x cubed. Now, usually in my classes where I would say, are we done now? Well, the answer is no, because we have to take into account that when we take our antiderivative, there's going to be some constant that is added or subtracted to it, which of course that constant could be 0. And it's because when we take the derivative, right, if we take the derivative of 4x squared plus 2, 4x squared, or 4x squared minus 266, these would all give me the same thing of 8x whenever I took my power rule, used my power rule for the derivative. So when we do the antiderivative, we have to take into account that there's some constant c that could be added to this. And another thing I kind of want to point out is when we're doing these parts where we split it into the antiderivative of the first term, second term, and third term, is depending on how this is set up, you may end up with multiple constants. But the idea with this is that we could then combine those constants into one single constant. For problem 8, we're doing the exact same thing. So now we have this function, f of t equals t to the 5th power minus 3t cubed plus 4 divided by t squared. Now, we don't have a way that we can easily find the antiderivative for this in its current form. So what I'm going to do is I'm actually going to split this into t to the 5th over t squared minus 3t cubed over t squared plus 4 over t squared. And then I'm going to do some simplification. So if I were to take t to the 5th divided by t squared, this would be t cubed, because you subtract the powers. This one is going to end up being minus 3t, and then this one will stay as 4 over t squared, but I'm going to rewrite it with the t to the negative 2 power. So this will be plus 4 times t to the negative 2. And now I can actually find my antiderivative, f of t, by taking the antiderivative of the first term. So this is going to be t to the 4th. And then I'm going to divide by that power of 4. This one, if you think of it as t to the 1st power, I'm going to bring the power up by 1. So this is going to be minus 3t squared divided by 2. And then for the last one, we have plus 4. And then I have t to the negative 2 power. So I'm going to take that up by 1. This is going to become t to the negative 1. And I'm going to bring down that negative 1, which is going to make this term negative. So now kind of rewriting this, just to kind of clean it up a little bit, this will be 1/4 t to the 4th power minus 3/2 t squared. And this one is now going to become minus t to the negative 1, which is the same thing as saying 1 over t. So this is going to be minus 4 over t. And of course, again, we have to consider that we have this plus c that we need to account for. Problem 9 says to evaluate the integral 4x cubed minus e to the x dx. So whenever we're doing an integral like this, first of all, this is an indefinite integral. But second thing is, if we ever have the integral of some function plus or minus some other function, we can actually treat this as the integral 4x cubed dx minus the integral e to the x dx. And whenever we're taking an integral, what we're first going to do is we're going to figure out what is the antiderivative of this first term. So in this case, just like before, this x cubed is going to become x to the 4th power, and then we're going to bring that 4th power down. And then, of course, we just leave our 4, because we can really pull the constants out. They're not going to have any impact. So this would be 4 times x to the 4th over 4, which is going to be 4 over 4 x to the 4th. So these 4's are going to cancel. Next, we're going to take minus the antiderivative of e to the x. Well, the antiderivative of e to the x is e to the x. Now, because we're doing an indefinite integral, we don't have any values or limits for our integration. So in this case, we're just going to have some plus c, just like before, because our antiderivative of x to the 4th, so in this case 4x cubed, would be plus c. And the antiderivative of e to the x would be plus c. And then we combine those c's, so we end up with x to the 4th minus e to the x plus c. For problem 10, it says we want to evaluate the integral from 1 to x 4t plus 2t squared dx. Now, same thing as before. I'm going to take this as the integral of my first term plus the integral of my second term. And while I'm at it, I'm going to pull those constants out because I can do that as another step. So this is going to be the integral from 1 to x. I'm going to pull that 4 out. T, d, this should actually be, so dx. Plus 2 integral from 1 to x, t squared, dx. So as before, what I'm going to do is I'm going to bring my 4 down. I'm going to take the antiderivative of t. So you can think of this as t to the 1st power. So this becomes t squared. And I'm going to divide by 2. And then I'm going to evaluate this from 1 to x. So when I did in class, I think I did evaluate this 1 to x, evaluate the next one 1 to x, but I'm just do it all together. For this next one, I'm going to add 2. Now I have t squared. So I take the antiderivative of that. This is going to be t cubed divided by, bring that 3 down. And now I'm going to evaluate this integral from 1 to x. So remember, whenever we're evaluating a definite integral, we're going to take, if we have some integral from a to b, f of x dx, this is going to be equal to f of b minus f of a. So I'm going to evaluate both of these in terms of x. This is going to be equal to, so this is going to cancel, give me a 2. So this is going to be 2t squared. So this is going to become 2x squared. Then I'm going to evaluate this one. So I'm going to have 2/3, so plus 2/3 x cubed. Now I'm going to evaluate for my lower limit of my integration by plugging in 1. So I'm going to get 2 times 1 squared. 1 squared is just 1. So this is going to be minus 2. And now I'm going to do the same thing here. So 1 cubed is 1. So that'd be 2/3. So minus 2/3. So now if I were to rewrite this, first things first, I'm going to put my highest power first. This is going to be 2/3 x cubed plus 2x squared. And now I just need to combine my constants together. So 2 can be thought of in terms of over 3 would be 6/3. So 6 minus 6/3 minus 2/3 is going to give me minus 8/3. Now before, when we did our indefinite integral, we had to add plus c because we have some constant that could be added or subtracted. And again, could be 0. But in this case, because we have the limits of our integration, meaning we're doing a definite integral, we don't have to add this plus c because the constants actually are taken into account when we do our evaluation of the limit. For problem 11, we want to evaluate the integral from 1 to e 1 over x dx. So just like before, we're going to find the antiderivative. So what is the antiderivative of 1 over x? Well, the antiderivative of 1 over x is the natural log of the absolute value of x. And then I'm going to evaluate this antiderivative from 1 to e. So just like before, I'm going to take my upper bound. This is going to be the natural log of e. Natural log and e cancel with each other. So this is going to be equal to 1 minus the natural log of 1. So of course, the natural log of 1 is equal to 0. So this one actually ends up being a pretty simple one. It just ends up being equal to 1. For problem 12, we want to find the answer for the integral from 0 to 2, y minus 2 times 4y plus 3 dy. So in this case, again, I can't find the antiderivative in its current form. So what I'm going to do with this is I'm actually going to distribute the y minus 2 into this, and this will give me something that I can actually find the antiderivative for. So this is going to be the integral from 0 to 2. So what I'm going to do is I'm going to distribute this and basically FOIL it out. So I'm going to do first, so I'm going to get y times 4y is going to give me 4y squared. Then I'm going to do my outer terms, which are going to be y times 3, so plus 3y. Then I'm going to do my inner terms, so minus 2 times 4y is going to be negative 8y. And then I'm going to do my last terms, which is going to be minus 2 times 3, which is going to be minus 6. And then don't forget your dy. Okay, is there anything I can combine? Yeah, I can combine 3y and negative 8y, which is going to give me negative 5y. So this is going to be equal to the integral from 0 to 2, 4y squared minus 5y minus 6 dy. Now, as before, I can take this integral now, and I can take the integral of this first term minus the integral of the second term minus the integral of the third term. So this is going to be the integral from 0 to 2. I'm going to pull that 4 out, and this is just going to be y squared dy minus 5 integral 0 to 2 y dy, and then finally minus 6, which I'm actually going to think of this as y to the 0. So I'll do 6, so minus 6, 0 to 2, and this is going to be y to the 0 dy. Now, we did actually talk about a rule where if you ever have the integral of, for example, just a constant dx, this would just be cx. And that's exactly what's going to happen. So let's actually find our antiderivatives so we can evaluate this. So the first one, we have 4 times, when I take y squared, I'm going to make this y cubed, so it's going to be y cubed over 3. Minus 5, y to the 1 becomes y squared, so this will be y squared over 2. And then finally, I have minus 6, and if I take y to the 0, if I take the power up by 1, it becomes y to the 1. And then I divide by 1, which doesn't change anything. So this would just be minus 6y. And then I'm going to evaluate the entire thing from 0 to 2. So just like before, I'm going to start with my upper boundary. So this is going to be 2. 2 cubed is 8. 8 times 4 is going to be 32. So this is going to be 32 over 3. Minus, now I'm going to plug 2 into y squared. So this is going to be 4. 4 times 5 is 20. 20 divided by 2 is going to be minus 10. And then finally, I'm going to plug 2 into this. So minus 6 times 2 is going to be minus 12. Now I'm going to subtract when I plug in the 0. So I plug in 0 to this term. 0 cubed is 0. This whole thing becomes 0. So I'm just going to leave it as minus 0. If I plug 0 into this, 0 squared is going to be 0. So minus anything times 0 is just going to be, technically it's plus because it's minus minus, but plus 0. And then last one, I'm going to plug in 0. And again, I'm going to get plus 0. So adding all this up together, I'm going to get that this is equal to negative 34 over 3, which is going to be approximately equal to negative 11.33, just repeating. So this will be minus 11 0.33333, on and on and on. For problem 13, we want to evaluate the integral from 1 to 9, 3t cubed plus t squared square root of t minus 7, all divided by t squared dt. So as before, we can't solve this one directly, so I'm going to take this t squared and I'm going to split it and divide into each of these different terms. So this is going to be equal to the integral from 1 to 9, 3t cubed over t squared, which is going to leave me with 3t. For the second term, t squared is going to divide t squared and be left with the square root of t, which I'm going to write as plus t to the 1/2 power. Now we have minus 7 over t squared, so this will be minus 7t to the negative 2 power, because the negative power brings it to the bottom. And finally, we have our dt for our integration across the variable t. So now what I need to do is I need to split this and then find the antiderivatives. So I'm actually going to do this all in one step. Normally, what we're actually doing is we're splitting this into the integral of 3t plus the integral of t to the 1/2 minus 7 integral t to the negative 2. What I'm now just going to do is I'm just going to find these antiderivatives, and then so what I'm going to do is I'm going to split it and find the antiderivatives at the same time. So the antiderivative of 3t, so right, pulled 3 out, so the antiderivative of t is going to be, 3t squared over 2. Plus, if I have t to the 1/2, I'm going to add a power to it. This is going to become t to the 3/2, and now I need to divide 1 over 3/2, which, of course, if I'm dividing by a fraction, it's the same thing as multiplying by the reciprocal. So this would be 2 over 3. For the next one, I have minus 7. This is going to become t to the negative 1, because negative 2, bring the power up by 1. So this will be t to the negative 1 over negative 1. So, of course, I'm just going to add this now so I don't forget it. That's going to make this plus. And then I'm going to take my limit my limits of integration from 1 to 9. Okay, so now what we're going to do, just like before, we're going to plug in our upper boundary values first. So this is going to be, I'm just going to write it out first, 3/2 9 squared plus 2/3 t to the 3/2 power plus 7 9 to the negative 1 power. And then we're going to subtract when we plug in the ones. So this is going to be minus 3/2 minus 2/3 and then minus 7, right? Because when I plugged in 1, this became 1 squared is 1, so 3/2. This one, 1 cubed is still 1, square root of 1 is still 1, so this became 2/3. And finally for this one, when I plugged in my 1, this was, actually, sorry, this should have been plus 7. Because when I plug in my 1 to the negative 1 power means divide by 1, and 7 divided by 1 is still 7. Okay, so now we just have to figure out what these values are. So plugging this in, we get 9 squared is 81. So we're going to have 81 for this term. This one, I don't know why I put a t here. This should have been a 9 to the 3/2 power, which this is going to be equal to 27. 9 to the negative 1 just means that this term here is going to become 7 over 9. And now we can actually figure out what all this is. So I'm actually just going to plug this in my calculator. So I have 3/2 times 81 plus 2/3 times 27 plus 7 over 9 minus 3/2 minus 2/3 plus 7. So plugging all of this in, I get a value of 1,306 over 9, which is approximately equal to 145.111. For problem 14, we want to find the integral of sine of x minus 1/3 x dx. So first things first, I'm actually going to do all the steps for this one. This is going to be the integral of sine of x dx minus, now I'm going to pull this 1/3 out, so this is going to be 1/3 integral x dx. So now we're going to find our antiderivative. So the antiderivative of sine of x, so think about what function, if I took the derivative, would give me a positive sign. And this is going to be a negative cosine, right? Because if I took the derivative of negative cosine, it would give me negative sign, which is positive sign. So this is going to be negative cosine of x minus 1/3. And now I take the antiderivative of x. So this becomes x squared over 2. And then, of course, because this is an indefinite integral, I have to add plus c. So then cleaning this up, I'm going to get minus cosine of x. I have minus x squared over 6 plus c. For 15, again, we're going to have another integral. This one is the integral of e to the x plus 5x cubed dx. So just like before, I will split this into the integral of e to the x dx plus, I'll pull that 5 out. So this is going to be 5 integral of x cubed dx. So now we'll find our antiderivatives. Antiderivative of e to the x is e to the x. Plus 5, now we take the antiderivative of x third, which is going to be x to the 4th power, and then bring my 4 down. And then finally, so this is almost the final answer, but now I just have to add my plus c. And this is what I was talking about earlier about how you could think of it as having multiple constants together combined at the end. Because if I did this integration here, integral of e to the x dx, this would be e to the x plus some c. Let's call it c1. And then when I took the antiderivative of 5x to the 4th power, this would give me 5/4 x to the 4th power plus c2. And then when you add your constant 1 and constant 2, we just get some arbitrary constant c. For problem 16, we need to look at the graph of our function g of x, and then we want to draw what the derivative graph of this function would look like. So we have our original function g of x, which I didn't draw into the grid lines or anything like that, because we're going to just kind of do it freehand. But you can see here what this would look like if you were actually doing this problem. So for the first part, we have to figure out where we're going from a positive to a negative slope. So right, what we want to do is we want to look at points where things change. So when we're drawing our derivative graph, anything that is in the first two quadrants, quadrant 1 or 2, these are going to be where you have positive derivative. Anytime you have a negative derivative, they're going to be in the 3rd and 4th quadrant. So looking at our graph, we're going to figure out, okay, where do we have a slope of 0? That is a point where we're crossing either from positive to negative or negative to positive. So I have a slope of 0 at this point, and I have a slope of 0 at this point. So then I would draw these on my graph. So I'm going to say I have a 0 here and a 0 here. And now let's look at what is the behavior to the left and the right of these zeros. Well, if I look to the left of this point here, I have a positive slope. That means I should be in the positive 2 quadrants of my derivative graph. So this would be g prime of x. So this means I'm going to have something like this, right? Because what's happening with this graph is that at positive, but I'm getting lower. So that means that it is decreasing. And then once I get to that 0, I now have a negative slope, which is going to be increasing. And then it's going to be decreasing until I hit this point here, where again, I have a slope of 0. And then to the right of this, I have a positive slope again. So it's going to be something like this. So this is what the derivative graph would look like for this function, which kind of makes sense because if you remember back when we first learned about this, whenever we have some function, every time we take a derivative, we're generally going to lose one of the curves. We had 2 curves here. Now we have a derivative with a single curve. Now, one other thing you do have to be careful about though is also when you have these graphs, you might end up having a saddle point. So for example, if I had a curve of something like this, where it goes to 0 and then continues on, when I would draw my derivative graph, this would be something like this. I have a negative derivative, I hit 0, but then I have a negative derivative still. So I stay in the negative part of the derivative graph. For problem 17, we want to use the graph of f of t that I've drawn here to graph f prime of t. So again, we have to consider what is happening with our derivative graph. So first things first, this one is only in the positive, so we're just going to focus on here. But we are going to have positive and negative slopes, so we'll have the 1st and 4th quadrant on our graph. Looking at our derivative graph, we have a positive slope for our first little section from 0 to 1. So for 0 to 1, we have a positive slope. But notice that it's constant. It's a straight line. That means that it looks something like this, right? It's positive, but it's not changing. It's not getting bigger. It's not getting smaller. Then what happens at 1 is now suddenly we jump to having a 0 slope. From 0 to 2, we have a slope of 0. And then from 2 to 3, we now suddenly have a negative slope. But again, it's constant. So this means we'll have something like this from 2 to 3. And then from 3 to 4, again, we have a slope of 0. And then last, we have from 4 to 5, actually from 4 to 6. So this is 4, 5, 6. We now have another positive slope. But again, it's a constant. So therefore, this one is going to be somewhere here. For 4 to 6, we'll have a straight line. So if we look at our graph, we have a line in the positive, then it goes 0, then it goes negative, then it goes back to 0, then it goes positive. But we have these major jumps. Why is that? Well, because if we look at how this graph is shaped, right, when we do something like this, this is not giving us a change in our derivative. We're going straight from a positive slope to no slope to a negative slope, right? So it's sort of like when we did our absolute value. When we had our absolute value of x, it looked something like this. So we went straight from a negative slope up to a positive slope. So if we were to graph that as a derivative, this would go for a negative, we would hit 0, and then suddenly we jump to positive. So in our derivative graph, this is why we have these jumps, because we don't have some nice smooth transition from positive to negative, right, where it's continuous, or where it goes from negative to positive, where again, it's continuous. For our last 3 problems, were just some quick concept problems where we want to check whether they're true or false. Now, on the exam, if it was true or false like this, you would just put true or false and then move on. But what we're going to do is we're going to actually correct it to see what the answer should have been. So number 18 says, if f and g are both differentiable at x, and if g of x is not equal to 0, then f divided by g is differentiable at x, and d dx of f of x over g of x is equal to f prime of x over g prime of x. So in this case, this would be false. We cannot say that the derivative of f of x over g of x would be equal to the derivative of f of x over the derivative of g of x. Why is that? Well, because this is actually confusing 2 rules together. We have our quotient rule, which describes the derivative of some f of x over g of x. And then we have this, which is actually from our L'Hopital's rule. So if we wanted to correct this, what this actually should be equal to is g of x, f prime of x, minus f of x, g prime of x, divided by g of x squared. Or the way that we often referred to in class was gf prime minus fg prime over g squared. For number 19, it says, if I have the integral from 7 to 7, x squared dx, this is equal to 0. This one is true, and that is because if we have any integral from some value a to some value a on any function f of x, as long as it's continuous, or I guess at that point, it exists at that point, then this will always be equal to 0. Now, why is that? Well, let's think of it intuitively. If I'm taking the integral, which think about your Riemann sums, where we take some function and we slice it into smaller and smaller and smaller rectangles. Well, if I have from a to a, this would mean that I have a width of 0, right? I'm not going from point A to point B, I'm going from point A to itself A, meaning I have a width of 0. So when I try to take the area of that rectangle that describes that very small area, there is no area because it would be base times height or width times length, and the width would be 0. 20 says, if f prime of c equals g prime of c for every x, then there exists a constant c so that for every x, g of x just equals f of x plus c. And this one is true. And it's because if I have some function f of x, let's do it like this. And then I have some function g of x. What we're saying is that if my f of x and g of x have the exact same derivative at every single point x, that means that when I have this starting point here, I'm going up by a particular slope, g of x is going up by the same slope. When I hit a slope of 0 here, g of x hits a slope of 0 here also. So same thing here. Basically what's happening is everything that one function is doing, the other function is doing also. So the offset of this is just going to be plus some value c. So what this means is that I basically have 2 functions, f of x and g of x, and this f of x is actually going to be equal to g of x plus that constant c. Or you could write it the other way and you could put the constant with g because that c could be the negative value, right? So if this has a value, let's say c is 2, if f of x is 2 above for every value, then you could say that g of x is 2 below for every value. So that's the end of our calculus review for our final exam. If you made it this far, thank you for watching. Hopefully you'll subscribe and continue watching other videos to keep learning more about math and stats topics. If you are one of my students, I just want to remind you that we do have another comprehensive review that we'll be doing with different problems, meaning that we'll be able to practice more of this stuff and it'll be something new. But otherwise, I hope everybody learned a lot from this. I hope it was helpful, and let's continue learning math and stats. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.